This paper is a facelet bank for fast portrait manipulation by Chen et al. Face manipulation has been a very interesting topic in computer vision and graphics. However, previous methods have mainly been devoted to face beautification, debeautification, expression manipulation, and age progression. Different facial structures and different attributes need special manipulation techniques. For example, these two men have different facial features, so they would require different manipulation techniques. Most approaches were designed for individual tasks, and if you wanted any new solutions for effect generation, it requires you to have experts with domain knowledge. There are some possible solutions to this problem. One possible solution is direct regression. In this method, you directly regress the input and ground truth image after edit. However, this requires labeled paired data, and that is often unavailable or it requires a lot of human labor to generate. So, if you want to create any new effects, you can't use direct regression very easily. Another possible solution is generative adversarial network. This is good for set-to-set unsupervised learning, and it uses cycle-consistent laws to preserve the image content as well as adversarial laws to transfer attributes from one set to another. However, it is difficult to train, especially for new effects that require system component modification. And if you don't train it properly, the results would be unrealistic and easily noticeable. One other possible solution is deep feature learning, which learns how to change the image attribute from two different sets using the deep feature of the two image sets. The problem is that the framework is not end-to-end, so it can't be globally optimized. Also, it requires heavy computations, even during testing, because it involves hundreds of face warping and convolution operations. The solution suggested in the paper is a flexible, high-quality output network for face manipulation. It has an encoder-decoder architecture and is specially designed to allow users to control the level of effect, thus enabling interactive face manipulation. The facelet bank framework that they propose only updates the middle convolutional layers to generate different effects instead of redesigning the entire framework completely. In this example, the subject is made to look younger in one image and given facial hair in another. There are also other ways to manipulate the image that will be discussed later. There are four main contributions from this paper. 1. They propose a set-to-set CNN framework for face manipulation that does not require paired data in training. 2. Their system is developer-friendly because you can generate different effects by simply updating a few convolution layers. 3. Their method is able to regularize noisy labels because it benefits from the local prior of convolution layers. And finally, their experiments show that this approach can handle a wide range of face effects with fast speed.
Now we begin with proposed method. Suppose there are two face domain X and Y with different properties. Our goal is to shift image of domain X towards domain Y without guidance from any paired data. As for face manipulations, we want the algorithm to produce intermediate results so that users can control the strength of operation, such as smoothness of the skin. This process is represented as Z. Okay, so in here, Z is consists of X, where X is an input and output image, and also with lambda, where lambda is control the strength, and function O in here is denotes the operation that changes X from domain X towards domain Y. Note that domain X and Y usually differ semantically, so O can be highly complex. In order to simplify O, we instead define the operation O' in a deep space and change the equation above to this equation. And to one extreme, if psi capture enough rich semantic information, and then O prime can be further simplified as linear shift in a deep space, which leads to this equation. Okay, so in here we use 5 convolutional layers to construct C to represent phase attributes at different levels. So here we use ReLU 3, ReLU 4, and ReLU 5 are jointly used to represent C. Okay, and now we try to train a fixed decoder network D to decode C to obtain the final output. The decoder D has reverse architecture of the encoder E, except for concatenating and manipulated features to the corresponding layers. We use the following loss function to train D. So this is the loss function that we use to train D. And we also observe that pre-training of the decoder with this formula. Okay, so this is the overall structure that we use. The network architecture is illustrated by this figure, which is composed of an encoder E. This is the encoder E that transforms all the images, and then we transform image to a deep space by using a convolutional neural net that estimates the domain direction shift of delta V, and then the decoder that transforms the operated deep feature back to image. And we begin to learning facelet banks. This learning facelet bank is useful to estimating delta V, which requires cancellation of all factors except for the target attributes. So in here we could see that delta V, and then after that we try to generation pseudo labels. In here learning V is difficult as we don't have paired data to infer delta V for each training sample. We average neighbor of each training sample of both domains to construct the attribute vector. So this is the attribute vector. And after that we try to search or to make the network designs. Since delta V prime relates strongly to the deep feature, we reuse the extracted deep feature by setting the input of V to V with the function of E. We stack 3 fully convolutional layers with ReLU activation to capture the nonlinearity relation. In this way, V can be learned as the equation below. So this is the V, and finally we start to make more analysis of the facelet banks. Although our facelet banks learns with the help of pseudo paired data delta V prime, it has additional advantage compared with directly using delta V prime. So in terms of noise resistance, our facelet banks can even outperform the pseudo label of delta V prime. To demonstrate it, we compute the heat map of delta V by using following formula, where I is a set from 1 until H and continue with G, same also as a set of 1 until W, and K is a set from 1 until C, denotes the row, column, and channel of index respectively. Okay, in figure below,
They used PyTorch for implementation. PyTorch is a deep learning framework which can reduce the amount of coding. The coders train using the Adam optimized convergence technique. The dataset used for training collects image from Cerebr's 90% image, portrait, harem, and Flickr's images. Landmarks and attributes were calculated using this function. Evaluation of this approach. Attribute direction delta V greatly affects the result. Simple method of global and KNN has problem. Case of global method. Input image with a many change with dataset. It will incorrect result. In this example, the position of beard is wrong. Case of KNN method. Improve this problem, but some result skin color may not be reproducible. Since this method learn the relationship between the mouse and the corresponding beard, so correct results are obtained and no major problem are found. It has already been shown that different levels of layer are complementary to each other, so good results can be obtained by using multiple different layers. In this example, it's take of removing face hair. In B image, most of it has been removed, but it is not perfect. In the C image, layers 4 and 5 are used and the results are better. In the D image, use all layers to produce complete results. Now I talked about different operation strengths. Deep feature and the shift are calculated once. Then you can calculate the intensity layer. So you can calculate image of different intensity at high speed. Those are results with different intensities, but the result may be slightly unnatural if the intensity is strong. This is compared with another method. Quality overall has better result than cycle GAN and DFI, and in the higher result, our approach's results are better than DFI. Speed is almost as cycle GAN, and 3,371 times faster than DFI approach. Let's see an example of adding a beard to a woman's face. This is a little bit illegal case of effect. You can see that better results are obtained than DFI. DFI depends greatly on training set samples, but their method is mass-beard relationship and the results are better. Conclusion. They proposed a framework for genetic face manipulation. As a feature of this framework, it is possible to run change of attribute of face from only 2 images. And the person labeling is unnecessary. And the amount of calculation is not large. Thank you.